Are there any questions on whatever has happened so far? Any questions from anyone on the first chapter? Because we have just finished the first chapter and I will start the second one today.
Sir, I have a question.
Yes.
So there was these three probability measures that we talked about. The first one was the P vectors, that is the actual probabilities, and then there was this linear pricing measure, the pi vector, and there was this risk neutral probabilities, right? So when we are computing this pi vector, this linear pricing measure, then we do not need to know these two probabilities pi's. It is kind of independent of those. Again, the new risk neutral probabilities is also independent of those two probabilities. So what is the kind of role that these two probabilities are playing?
Okay, so first of all, you don't really need to think about them as two separate things. I and Q are essentially the same. Q is a special case of pi. Both are dictated by the market situation, by the payoff matrix. We have solved it last time explicitly for Q. The Q is really a solution from the payoff matrix. Pi is just a
Yes.
weaker version of that, where you also allow zero probability in some states of nature. But
Yeah.
we have seen that if we allow zero probability in some states of nature, some of the inclusions will not be strict. Because
Yes.
what we really wanted was that no arbitrage, law of one price. That picture, I think maybe if I start sharing the screen and go back to the picture. So can you see my screen now?
Yes, sir.
Yeah.
Yes.
So basically, this was the situation when we allowed some of the pi probabilities to be zero in some of the states of nature. So these inclusions were not strict. But in a smart, efficient market, what we really want is that the law of one price and no arbitrage opportunity should be equivalent conditions. So to show their equivalence, we needed a further restriction on pi, and that gave us Q. And once we restrict ourselves to strictly positive probability or Q, then later on we are able to show that Q is completely determined by the market conditions and it is not linked to the P probability, which is the subjective probability of existence.
Yes. So what is the kind of role that the subjective probabilities are playing?
Yes, so that's what we will explore today. So when an individual is coming into the stock market, the individual knows that my perception is P, so my utility is dependent on this probability P. So his utility calculations, utility under uncertainty, which is expected utility, will involve P. But the market is deciding on the prices depending on Q, because Q is actually a pricing measure, it's not a probability. So how does these two interact? We have started that discussion last time by talking about the state price density. We will now use it more explicitly in the individual investors optimization problem.
Okay.
So this is what is going to happen today.
Okay.
Okay. So before I start that discussion, last time we actually finished chapter 1 and there are some exercises and examples which I want you to study. So you can now see the exercises and the examples on the top of this page. So I want you to do these exercises 1.10, 11, 12, 13 and 18 and also the two examples 1.8 and 1.9. These are all from Pliska's book. So you should be able to access. Okay, so then I think it's time we start with chapter 2. So last time we finished with something like a regression model, which we call the capital asset pricing model, that I said that I will get back to it again in a more formal setting, which will happen after I talk about the optimal investment problem of an individual investor. So to understand about the optimization problem, we need to understand what is the objective of the investor. The objective of the investor is basically consumption tomorrow on day one. So I invest on day 0 and I consume on day 1. Of course, consumption is uncertain because a state of nature will be realized tomorrow. Now, how do I evaluate my consumption? Or how do I evaluate my alternative consumption possibilities? So for that, the payoff function or the objective function of the investor is called a utility function. So we define what is called a utility function, which is a mapping from the set of consumption possibilities and the states of nature to some real number. So this real number is called the utility of a particular consumption portfolio in a particular state of nature. So basically what we are looking at is evaluating V1, but because V1 is uncertain, so we need to look at expected return. Are there any questions?
But actually, your voice is breaking.
Voice is breaking. I see. Okay. Is it better now? Because it is raining very hard in my locality, so there might be a problem with the internet. Is it better now?
Yes, sir.
Yes.
So I will try. If necessary, I will repeat things because I cannot help it. It's raining very hard. And whenever it rains, I can see that the internet connection becomes weak. So I will try to do it the best I can. But if there is a problem, just stop me and I will repeat whatever I said. Okay.
Yes, sir.
So I was talking about the utility function of the investor, which is the objective function. And that objective function depends on consumption and the states of nature. And it maps the consumption and states of nature into some real number. Is it clear?
Sir,
Yes.
so can you explain what is meant by consumption of an investor?
Okay. So we have been discussing the problem of investing on day 0 and consuming on day 1. So I invest today. I have some initial wealth V0. I invest it in the bank or in the stock market. That was our investment problem. And tomorrow, the actual value of V1 will be realized depending on the state of nature. So whatever state of nature is realized, that will give me some return, some total return, which is the realized V1, which I am going to consume. Okay, is that?
Okay. I mean, the extra amount which I am getting tomorrow is actually my consumption, like the gain.
No, not only the gain, the whole thing. So suppose today I start with 1 rupee, that is my V0, and I invest it in an optimal manner. And tomorrow I get back, say 1.1 rupee. So then I'm going to consume 1.1 rupee, not only 0.1.
Okay, so the value of tomorrow will be my consumption.
Yes,
If I am an
V1.
investor.
V1 will be my consumption.
Okay.
Precisely V1 will be my consumption. So today I am investing V0. So maybe I could have consumed it today, but I don't. I keep it for tomorrow. So I invest V0 today so that tomorrow I consume V1. But how much is V1 is not known to me on day 0 because V1 is dependent on state of nature. So in
Okay.
fact, it is written here clearly. So this is the utility function. So if you look at the screen now, the utility function is utility of consumption C at state omega. Okay. Now, we usually assume that any person prefers more to less. So if I get more to consume, my utility is higher. So I always assume that del U del C is positive. That's the first assumption on the utility function. It's a very standard assumption and almost always taken. There is a second assumption also, which says that my utility function is concave. What is the intuition of that? The intuition is, if I have 1 unit for consumption, so I start from 0, I get 1 unit of consumption, my utility increases certainly. Then I get a second unit of consumption. Again, my utility increases, but the increase with the second unit will not be as great as the increase with the first unit. So when I have got nothing, if I get 1 unit, that adds to my utility a lot. And once I've got 1 unit, then the second unit gives me additional utility, but it is less than what I had earlier. So that's the concavity assumption, which is put here as a second derivative condition. Is this clear? That I'm saying that as I get more and more, I value the increment less. So it's like if I'm already rich, some additional income is not going to add to my utility too much. But if I'm very poor, then that same additional income would be a great thing for me. Clear? So just keep saying yes or something, because I don't know whether you have been able to hear me. Because the voice is breaking sometimes. So just keep responding so that I know that you are with me. All right?
Yes, sir.
Okay. So how do I evaluate my utility? Because my utility is dependent on something uncertain. So it's a random variable. So what I do is we look at expected utility. And what is my expected utility in this investment problem? Very simple. I look at utility of V1. V1 is my consumption tomorrow, which is a random variable. So I calculate expectation of UV1, and the expectation is calculated under my own probability P. So this expectation is a subjective calculation. So I can simply write it out as a summation, because we have a finite state of nature situation. So I can write summation over omega, P omega, U at V1 omega, comma omega. You see, you have to remember that I am allowing omega to be an explicit argument in the utility. In some situations, what we do is, we do not allow omega here as a separate argument. We only allow omega to enter into the calculation through V1. These two are different things. Omega entering into V1 is only dictating the value of my consumption tomorrow. But omega directly entering into my utility function can also change how I value my consumption tomorrow. So one omega and one role of omega is to dictate the quantity of consumption. The second role of omega could be to dictate how I evaluate that quantity. So here, in a general setting, we are allowing both. But as you will see shortly, in many examples, what we will do is, we will make the utility function independent of omega directly. So we will basically ignore this second argument and only enter omega through V1. Is this distinction clear?
Yes, sir.
Yes, yes.
Because it's a very important distinction. You see, one is that omega can control the value, and the other is the omega can also control how I evaluate the value, how I get utility out of that value. It is like, if it's a rainy day, my utility function can be different. That is what this second omega can do to me. If I don't have this omega here, only have it here, then my utility function has to remain the same, whether it's a rainy day or a sunny day. So for simpler exposition, we will often assume that there is no second omega. It's a simpler utility. But you must remember that whatever we are discussing is actually true, even if we allow this second omega argument to come in explicitly. And there will be real life situations where this will be important. So this is the setup that you need to remember. Okay. So with that utility function and the expectation problem, we now formally define what is called the optimal portfolio problem for the investor. OPP, optimal portfolio problem. So what is the investor going to do? He wants to maximize the expected utility given his initial endowment. So we assume that today's value V0 is coming out of his pocket. He is investing the money, and that quantity is small v. So small v is an input. Given the input, the optimization will happen. And what is the maximization going to happen over? What is the domain? The domain is all the portfolios, all the trading strategies. So it is a maximization over all possible H. Of course, so far we are only allowing H's with positive arguments or non-negative arguments. So all the elements are between 0 and 1. Later on we will relax that assumption, but for now we have this 0 to 1 bounded portfolio weights or trading strategies, and we maximize over that set. And we can simply rewrite it in the following way to make the role of the stocks explicit. If you remember that discounted value expression earlier in chapter 1, you can see that this is same as saying I maximize expectation of utility of this argument B1 times V plus summation Hn delta Sn star. Okay, so this is written in terms of the original endowment plus whatever gain I can make. And B1 I take outside because B1 anyway will be the numerator or the discount. Remember, B1 is 1 plus R. Clear?
Yes, sir.
Yes, sir.
Okay. So now there are two important results. These results we need to understand. First result is the solution to this optimization problem does not exist if and only if there exist arbitrage opportunities. Probably we want to write it in the contrapositive way. We will say that the solution to 2.1 will exist if and only if there are no arbitrage opportunities. You see, we are still working with the earlier structure that we don't want arbitrage opportunities. We want that a risk neutral probability will exist and see what are the consequences of that on our optimization problem. And that is the result B. Result B says the same thing in terms of the risk neutral probability existence. So the solution exists if and only if there are no arbitrage opportunities, and the solution exists if and only if there is risk neutral probability. So these are the two important results for us now. And we need to see how they will go through. Okay. So what we will do is we will explicitly try to solve this optimization problem, and looking at the solution of that algebraic optimization exercise, we will connect with these results. The results will come to that. Okay. So this is a constraint optimization problem. So a constraint optimization problem where V0 is equal to small v. We include small v here, so it becomes an unconstrained problem now. And the second objective is the one that we are going to use. What do? We find the first order condition. So the first order condition gives me for every n, for every stock, I take the partial derivative and I get expectation of B1 U prime V1 delta Sn star equal to 0. So V1 is nothing but a shorthand for this whole thing in the second bracket. So I just don't want to keep writing it all the time. So I keep it here. Remember that even though I had n capital N plus 1 variables, I have wrote it in the discounted form so that H0 is already subsumed. So now my optimization problem is only on capital N many arguments, each of the stocks. So I am solving H1 up to H capital N. H0 is already there by substitution. Is that clear?
Yes, sir.
Yes, sir.
So through that substitution, I have reduced the dimension by 1. So this is my first order condition. And remember that for the risk neutral probability, we already had the second condition. So if I have a risk neutral probability, I know that this must happen. So this is an additional equation that I can use if I allow risk neutral probability to exist. So the way we are going to construct the solution, that's exactly what we are going to do. We are going to show that these two things are equivalent. Existence of solution and existence of risk neutral probability. So suppose we start with that. We have the risk neutral probability. So I have this equation. And from the first order condition, I have this first equation. I have two things to work with. So what do? I do the following thing. I show that, okay, so I can actually set my Q to be proportional to PB1 U prime. Because see, in the first equation, B1 U prime summation over P omega B1 U prime delta Sn star is 0. So P B1 U prime is orthogonal to delta Sn star. In the second equation, by similar logic, Q is orthogonal to delta Sn star. So I can say that these two must be proportional. So I say that Q omega is proportional to P P1 U prime. And of course, I need them to sum up to 1. Is that clear?
Yes.
So I construct an explicit solution. So that's the first result that I want you to look at. The result is that if HV is a solution to 2.1, so if it's a solution, then I will get an optimal H. Then it must be so that Q is equal to PB1 U prime by expectation of B1 U prime. How did I get this denominator? I get this denominator by the normalizing condition. If I just sum up over all the omegas, I will get that, because I know that summation over Q is 1. So if I sum up, the proportionality constant here will turn out to be 1 by expectation of B1 U prime. It's a very simple one-line algebra, so I think you can easily do that. So, see, what have I achieved? I have achieved a lot with this one equation. I can show that if there is a solution to 2.1, then I have a Q. I explicitly get an expression for Q. And because it's a very simple equality, I can also say that if there is a Q, I will be able to construct a solution. Is that clear already, or?
Yes.
Yeah. So I think this is very, very simple. So this is some kind of a calculus you have done in your first year probably. Now let me bring back my state price density. So L omega, my state price density, is Q by P. So that must be proportional to U prime, because Q by P here is proportional to B1 U prime. So if I take B1 to be a constant, then Q by P will be proportional to U. And this is called marginal utility. The first derivative of the utility function is called marginal utility, which is the incremental utility, del U del V. Okay, so here is one nice connection, that if I start out with an investor's utility function and a probability function, then how do they link up? These two are not independent. The state price density, which is Q by P, has to be proportional to the marginal utility. Why is that so important? It is important because I know that Q is market determined. A individual investor's perception does not have any role in determining Q. The investor comes with an input of P and the utility function U. Now, if the optimization problem needs to be consistent, then the utility function and the subjective probability must also be related or linked to each other. And what is the link? This is the link. The state price density must be proportional to the marginal utility. This is required for the consistency of this solution, of this whole problem. Is that clear?
Sir, I have a question.
Yes, sir.
Yes.
Yeah, so you are saying that P omega B1 U prime, that thing is orthogonal to that delta Sn star, and again we have this Q is also orthogonal to that delta Sn star vector. So then you concluded that you must have these two kind of equal or proportional to each other, but that is only true if we are talking, but there might be like, since this is a r to the power n vector, so there is like, you are considering only one subspace there, and you are taking one orthogonal vector to that. So there might be many orthogonal vectors.
Recall that earlier completeness result, that the rank of the matrix is equal to the states of nature. Recall that rank condition.
Okay.
I am using the rank condition.
Okay, so these are all under complete markets.
Yes, yes. See, if I don't have complete market, then I don't have strict inclusion. See, I started today's discussion with that set, that Venn diagram. So I want that Venn diagram to be equivalent, remember?
Okay.
So that equivalence happens only for a complete market with a unique risk neutral probability, and then the payoff structure will have the rank, same rank as the states of region.
Okay. Okay.
So I am working with all that setup. This is the nicest possible setup. No, your question is valid because there is no guarantee that such a nice setup actually is realized in reality, in real life. But so far, whatever theory we are developing is being developed with that nice setup.
Okay.
So later on, we will try to see what happens when we depart from the nice setup. So we look at the departures, but the departures becomes very messy. So before we go into that, we want to see what are the nice results we can get from the very efficient, very smart market strategy. All right. So let us continue with the discussion. So basically what I do have so far is Q is proportional to PU prime. Now Q's are objective or fixed. But that's what I was saying. So I must have P is essentially changing with 1 by U prime. Plus Q is market determined. The investor has two things, P and U. So this P and U must be very, very nicely tied together. And that tying together happens here. That's what we have seen from the state price density. And this is what we are going to use. So we have state price density proportional to the marginal utility of terminal wealth. Conversely, if I have a Q, I can always find a utility function U and small v such that a solution will exist. Why do I know that now? Because now I know that the utility function is not arbitrary. The utility function is already tied down. The utility function is already tied down through the proportionality here. So it will be like solving a differential equation. Or I can choose a U function smartly. So that's what we will do here. So, but first, here is a definition. A model is viable. A model is viable if there exists a U utility function and small v such that the corresponding optimal portfolio problem has an optimal solution H. So whenever we have such pairs of U and V, we have a solution. If that happens all the time, then we will say that the model is viable. So again, this is something like a consequence from the completeness of the market. Earlier, we defined what is the completeness and what happens in a complete market. This is a very important consequence of a complete market. In fact, a result that follows directly from here is the securities market is viable if and only if there is a risk neutral probability. Now I think it's obvious, so I really need not talk about it more. What I will do instead is I will now talk about a choice of utility function. So the choice of the utility function is, we already have this relation here that U prime is proportional to 1 by P. So I choose my U function. This is U, this is not U prime. Okay. So just to tell you that this is wrong, this is not prime, there is no prime here. It is U. So I choose my utility function U C omega as C times Q by P B1. This will satisfy my condition of proportionality. And it's a very nice, simple utility function. Okay, is this clear? That this choice will give me the consequence I want?
Yes.
Yes, sir. Yes.
And then you can immediately check that the expectation under P of the portfolio utility will be same as expectation of the portfolio under Q. So U is a particular form, C times Q by P. So when I put it here, what will happen is when I sum over P, the P will cancel each other. So it becomes a sum over Q. So it becomes a risk neutral computation. Utility function is gone. So I have only whatever is inside in the portfolio. And I know under the risk neutral probability, delta Sn starts as 0 expectation. So the expectation under Q now must be small v plus 0, which is small v. Is this clear? So I'm just omitting one or two lines of simple algebra, but for you it should be absolutely trivial. Is it clear?
Yes.
So expectation of utility under P is same as expectation of value under Q because of this particular choice of utility function. And then we have the risk neutrality condition that the expectation must be equal to the initial wealth. Remember, under risk neutral probability, we have shown that delta SN star must have zero expectation. So under Q, we cannot expect to gain anything. Our expected gain will be zero. So when I do the utility calculation, because my utility calculation is linked to the P through risk neutral probability, I still have the same condition that when I am operating in an efficient market and I work with a consistent utility function, remember utility function is not arbitrary anymore. It has to be consistent with P and Q. With a consistent utility function, my expected utility also must be equal to the initial wealth. So that is the most important takeaway from this, that even though I allow investors to have any belief they want, any P they want, their utility function will become tied down with the P. It will adjust between the probability and the marginal utility in such a way that their expectation calculation remain consistent with the efficient market tenets or the Martingale property. So this is actually the Martingale property. I have not defined Martingale formally, but I think we mentioned it earlier once. Is this clear so far?
Yes.
So what I have done so far today is we have endowed the investor with a utility function, defined the optimization problem for the investor in terms of choosing their trading strategy. We have shown through construction that solutions, existence of solution is equivalent to the efficiency of the market and completeness of the market, that the solution will exist if and only if there are no arbitrage opportunities, and solution will exist if there is a risk neutral probability. Not only that, we have also seen that the utility function is cannot be arbitrary. The utility function is actually linked to the state price density, and hence we are able to choose a particular type of utility function, and that will give us the consistency with the efficient market Martingale property. So even though the investor may think that I can do anything I like, the investor is eventually tied down through the utility function and probability linkage, so that the investor's perception is consistent with the Martingale. It sounds very strange, but in a very smart, efficient market, that is what is going to happen. So in real life, this does not happen because many of the assumptions that we have taken in the past are not exactly true. They do not carry over. So there are a lot of departures from this in real life. So one very important avenue of work is to find out what are the consequences when we relax one of these assumptions. So we relax one assumption and see what happens. Then we relax some other assumption and see what happens, like both theoretically as well as empirically using data. All right. So for now we are in the ideal world. So we have all these linkages and the nice utility function, but we also need to be able to compute the optimal portfolio for an investor. And remember that number of stocks, the capital N, can be very large in real life. And also possible states of nature, the size of that set can also be very large in real life. So it could be a very large matrix system to be solved. So what we do in reality is we break this optimization problem into two steps. What are these two steps? See, the main problem is I want to maximize over the set of all the trading strategies. Through this expectation, I want to get to the utility, the optimal expected utility, which is a real number. So this is my real problem, actual OPP problem. But this might have a very big dimension, very big matrix to compute. So what we do is we break it up into two steps. One step is where from the trading strategies, we map it to the set of all attainable wealth, all possible V1. So from the set of trading strategies H, we map it to all attainable wealth V1. What is the advantage? The advantage is that V1 is a distribution over the real numbers, same as utility, because V1 is in the same unit as consumption. And the next step is, now that I have mapped it to V1, I now do the expectation over V1. And from the set of attainable wealth, I move to the real line. So the matrix problem, in the first step, I bring it down to a vector problem. And then the vector problem, I get into the scalar solution. So that is how the risk neutral computation algorithms usually work. Because in real life, both capital N and capital K are pretty large. So big matrix computations can be broken down and simplified in two steps. Okay, so this is the risk neutral computation strategy.
This expectation is taken over what?
Sorry?
The expectation of utility over all the map V1s.
Okay, the expectation of utility is for on the domain of V1. What is the domain of V1? So it's a real number for each state of nature, correct? Is that unclear? So these are the two steps. So maybe this will help. So step 2, I call it step 2. Step 2 is I go from the trading strategies to attainable wealth. So basically I find all the replicating values or all the attainable contingent claims. So identify trading strategies which replicates an attainable contingent claim. And the next step, I maximize over V1, expected utility of V1. That's the usual optimization problem. Does that clarify your problem?
Yes, sir. Yes, sir.
Sorry?
Yes, sir.
Yeah, okay, thank you. So just check whether the domain is getting easier or not. In practical sense, this breaking down is to make the computation easier. So this risk neutral computation breaks it into two steps from H to V, then V to utility. So in words, we will first find a claim V1 which maximizes utility, that's step 1, and then find an H going back. Because see, the market is complete. So given any V1 which maximizes utility, I can always find an H. Right? So all the claims are attainable. It's a complete market. So I can make my life easier by first solving for the second problem. That's why I call it step 1. Because I know whatever my V1 turns out to be, I can always find a corresponding H. All right?
Yes.
So now let us look at a simple example. It's overly simple, but we start with something easy. So we had two steps, step 2, step 1. So in step 1, we are working with V1. So step 1, this is the example. Suppose my utility is, remember that utility is proportional to the state price density. So I say that my U prime is lambda L by B1. This is coming from here. So let me scroll up. This is coming from here. U prime is proportional to L. Okay. So I write u prime equal to lambda L by B1. B1 is again for the numerator adjustment. Lambda is the proportionality constant. And then I can, of course, invert it and find out wealth W equal to u prime inverse of lambda L by B1. So if I have a specific form, then I can explicitly calculate. For instance, if I have this particular utility function, this is a very common utility function. Remember that in most of our examples, we will take very simple utility functions because otherwise calculations are going to be very messy. So the two common utility functions are this one that I am now talking about and the logarithmic utility function log W. Okay. So the logarithmic function and this exponential function are the two easiest utility function to work with. Easiest in the sense that they satisfy all the assumptions that increasing concave, and also they are very easy to use algebraically. So there is no special thing with them. It is just that they are very convenient to work with and they have all the properties. So this particular utility function will give me u prime equal to e to the power minus W. So this inversion will show me that W must be minus of log lambda L by B1. This is one particular choice of utility function with which we can do explicit calculations. It's an example of it. Now we have to evaluate lambda because lambda is the proportionality constant which needs to be evaluated in any Lagrangian problem. How do I do that? I know that expectation of W by B1 must be small v under Q. So that calculation I do. So I plug in the value of W from here and do the usual algebraic simplification. So this is something for you to do. So can you quickly do this and check that this is the lambda, this is the correct lambda. So take B1 equal to a constant 1 plus R. So this particular choice of utility should give me this lambda. Does it follow? Has any, okay, so please check and tell me if this expression follows.
Sir, the first step, that expectation over Q W by V1. How did we come to this?
Which one?
The first step, expectation of W by B1 is equal to V.
So this is under the risk neutral probability, right?
Okay, this minus this is 0 as such.
Yes, yes.
Okay. Yes, sir.
Yes, sir, it is following.
Yes, sir.
This is following, right? Yeah. So this is just algebra, which I'm very bad with, so I don't want to. So once I have this particular expression for lambda, then I will plug it back in to find out the expression for W and hence the expression for utility. So the expression for W is given by this thing. It looks slightly complicated, but remember that I can take B1 equal to 1 plus R. Then things will simplify. And the utility will be given by lambda L by B1. So this is the final expected utility. So if I work with that particular utility function, I can explicitly do this calculation, solve for the utility and the expected utility. Okay. To use this in an actual computation, suppose I work with this example. This example is example 2.1 on page 34. I have 3 states of nature. Again, R is 1 by 9. This is a favorite choice for Pliska. Q is 1/3 in all the states of nature, equal, but P is half, 1/4, and 1/4. There are 2 stocks, n equal to 2. Now I want to use this particular utility function, this exponential utility function. Remember that the state price density is given by the ratio of Q by P, so that can be easily computed. The utility calculation, we already have them here. So the utility for omega 1 will be this, omega 2 will be this, and omega 3 will be this. So these we can simplify. So these are the 3 possible utility values under at 3 states of nature. Okay. So this is my setup. So now suppose I am using a trading strategy H0, H1, H2. Because I have 2 stocks, so I will need 3 H values. So now I have this setup. This setup we have used before. So I am reusing same numbers from earlier. So I have 2 stocks. At day 0, one of them is priced at 6, the other one is priced at 10. And tomorrow, for the 3 states of nature, these are the corresponding pairs. So these are already discounted. So remember, we did that discounting earlier in an earlier example in chapter 1. R is, of course, 1 by 9. So then I have this expression. So if you are just following, you can just quickly do it yourself and satisfy that these are all correct. So I have this delta Sn star expressions for the 2 stocks. And then I can do this calculation. I already have the expression for log lambda or lambda. So I can use that expression and simplify. And we can show that lambda is equals this thing. It's a slightly odd expression, but it comes because I have to take a lot of logarithms. So that lambda will plug in W, and the wealth expression will be like this. Once I have that, I can calculate expectations. The expected utility will finally be equal to this. And as I have a complete market, this explicitly I can also calculate the trading strategies, optimal trading strategies here. They will be given by a solution to this equation, because W I have evaluated. So that will come out as a solution to these equations. Now, have you checked? So we have just gone through some algebra. It's a little bit tedious, but essentially very simple algebra. So does it all check out? Can you confirm? Can someone confirm?
Yes, sir. It seems fine.
Yeah, just do these calculations because these are also necessary because you have to have some practice. Of course, in real life, you will not do it manually. There will be a computer program, but it's good to know how to do these calculations. Okay, so we will take a break unless you have any questions. Are there any questions at this point? So today we have essentially looked at the optimal portfolio problem so far and worked out one very simple example. So I want to get on to the next thing after the break. So if there are any clarifications, please ask me. Okay, so if there are no questions, then we will take a break and we will start at 12 o'clock. It's okay?
Yes, sir.
Okay.
Yeah, so we'll restart at 12 o'clock. We just talked about the optimization problem and a particular example. So before I move on to the second example, let me tell you a little bit about the utility functions that we are going to work with. So let me share my screen. Okay, so can you see this page now on the screen?
Yes, sir.
Okay,
Yes, sir.
yeah. So there are a few utility functions which are very popular in math finance as well as in other microeconomic applications. So you may have done microeconomics before, so you may know this already. There is a class of utility functions which are the constant risk aversion class. And there are two ways you can define risk aversion. One is the relative version. The relative version is given by xu double prime by u prime equal to a constant. So this ratio to be a constant is the condition for constant relative risk aversion. And the possible utility functions which fall in this class are either log x, the logarithmic function, or u equal to x to the power rho for some rho and 1. Okay, so you can easily check that these are the two types of functions which satisfy this constant relative risk aversion condition, and conversely, these are the only ones which do so. A second definition of risk aversion is the absolute risk aversion, which is in our constant absolute risk aversion requirement, it is u double prime by u prime equal to a constant. So we don't have the x. Okay, and then the only possibility is in this class, and some, I think it could be e to the power minus lambda x for some lambda, things like that. So a class of utility function is essentially the negative exponential. There could be constants here, but those I am ignoring for the time being. So because of this constant risk aversion, which is a very important property in portfolio choice as well as some other microeconomic problems, this has been very popular in the literature. Also, they happen to be very convenient to work with algebraically. So you can typically find explicit solutions of your optimization problem if you take one of these candidates. So if you look at the examples worked out in this book, also the exercises, it will always be either the logarithmic function or the exponential function, because they happen to be very easy to work with and also satisfies this nice properties. So these are one class of utility functions which you will come across very often. Okay, so is this already known or is it something that you haven't heard before? How many of you need this? Many of you have done microeconomics, so maybe you have already done it. At least know the definition and some of the examples. Anyone? So as I said, you have to respond, otherwise I may not understand whether you are following or there may be an electronic problem.
Sir,
Yes,
we don't recall the definition of constant errors.
you don't recall this. So this was not part of
Not me.
microeconomics course. That's what you are saying.
I don't recall at least. So
Okay, that's fine.
yeah, I have forgotten or
So all I am saying is that these are very common examples. They have nice properties and also they are very easy algebraically. So in almost all the applications you will see, you will find one of them being used. This is just a note. Okay, so now let me get back to the main content. So we were discussing the optimal portfolio problem. So this was the example that we worked out. And for this example, the exponential utility function was used. Sorry, where is it? This particular type of function. You will see that you can also do similar calculations if you take the logarithmic function. You can also do explicit derivations for that. So this example also has the nice property that if you look at the trading strategy, you will find that the trading strategy is scale free. What is scale free? Scale free means it doesn't matter whether I start with 1 rupee or 1 crore rupees. My trading strategy has the same property, it remains the same proportion. So these proportions do not depend on how much money I start with. So these are called scale free problems, and this kind of utility functions are called scale free utility functions. This is actually a consequence of the constant risk aversion property. The constant risk aversion property implies that my solution will become scale free. So this is not in general true. This is not true for all utility functions. This property is true for this particular class of utility function. So that's why these class of examples are so popular. Okay, so now having done this constant risk aversion kind of utility, which are very nice to work with algebraically, I want to move on to the second important scenario, second important choice of utility function, which essentially ties up with empirical work. In finance, a lot of data work is done, obviously taking this normality kind of assumptions on board. Because for doing statistics, we most often take that assumption. It's very hard to do it otherwise. Now, in our portfolio optimization problem, we need a corresponding utility structure which will be consistent with our empirical assumptions. And the easiest one is the one that I'm going to talk about now. This is called mean variance portfolio analysis, where my utility function is dependent on only the first two moments. The first two moments of my portfolio. So utility function is just a function of the expected value and the variance. So that's why it is called mean variance portfolio analysis. this is again a very celebrated example which will lead to that capital asset pricing model that I mentioned last week. We will see that. Not only that, this will also tie in with our usual normality assumption, because if we are working with data and we are taking the normality assumption, then mean and variance are sufficient. So if my utility is characterized by only the first two moments, mean and variance, then it is nicely consistent with the normality assumptions in the empirical world. Is this clear?
Yes, sir.
Okay. So let us first define the optimization problem. So my optimization problem is the following, that I want to minimize the variance of the return vector. So in mean variance analysis, it is easier to work with returns rather than the value. So earlier we worked with V0, V1. Now we will explicitly work with the return vector. So we'll make it explicit very soon. It's not a problem. So the problem will boil down to trying to minimize variance such that my expected return is matching a target. So this rho is a target return that I want to achieve. Now I can achieve this target in many portfolios. There could be many solutions to this. But I want that one which also has the minimum variability in return. The logic is very simple. I like higher expectation, but of course I like lower variance. Now, if I want to achieve higher expectation, very often I will also have to take higher variance. So what do? So it is like my statistical hypothesis testing strategy. I fix my type 1 error. So I fix my expectation target, and then among all the corresponding solution portfolios, I find the minimum variance one. So I try to maximize power. Here I try to minimize variance subject to a target expectation. I could have defined it the other way around. I could have fixed my variance and then maximized expectation. It would have been a kind of a dual to this problem. But in empirical work, it is usually seen that solving this problem is easier because it's a simple linear quadratic problem. The objective becomes quadratic, so it is very easy to find optimal solutions. Do you know this property, this linear quadratic kind of setup?
Sir, I had a question.
Yes.
Sir, here essentially we are trying to find a minimum variance unbiased estimator of R minus rho. Is not it?
Yes, you can think of it like that also.
So we know how to compute that. Like we had the estimation theory for that.
So throughout this course, I don't think I'll be doing any mathematics which you don't know. The only thing you may not know are the stories that connect that mathematics with the corresponding market scenario. That's all. Most of the maths is very simple.
Okay, so we can think it of like that also.
You can?
We can think the problem like that also, right?
Yes, you can. Of course you can. Because that's the analogy I started out with. That's the typical type 1, type 2 error kind of analogy. You have also given a better analogy like the minimum variance unbiased. They all stem from the same kind of logic, doesn't it?
Sir,
Yes.
sir, here the return is the overall return or to particular to some stock.
No. Return is the portfolio return, overall return.
Okay.
So let me make it explicit here. So we will do it in a couple of minutes. So what am I doing here basically is, so suppose sigma is the variance matrix of returns. Okay. And E of Rn, so Rn is the vector. So I have capital N many stocks. Each of them has a return. So Rn is the mean vector. So the mean vector is E of Rn and the variance matrix is sigma. Sigma is capital N cross capital N. Now, the problem now can be recast in terms of this quadratic form, that I want to minimize f prime sigma f such that f prime ERN is equal to rho. So you see, f is basically my target H, my portfolio weights. I want to choose them in such a way that I achieve a target return, and of course I minimize the variance. And you know how to solve it. It's very easy then. An alternative but equivalent way of expressing the same problem, writing the same problem, is I want to minimize variance of V1, because essentially this f prime sigma f is the variance of V1, the value tomorrow, such that expectation is equal to V1 plus rho. Because if the return is rho, then the value, expected value, has to be V times 1 plus rho if my V naught is small v. So if my V naught is small v, then this expected V1 gives me the target return. So this is an equivalent way of expressing the same problem. So I will now use the typical Lagrangian language. I put this constraint, this is my constraint in terms of expected V1 inside here with the Lagrangian constant I write as beta. There is a reason why I am choosing beta, because later on I am going to match it with a regression problem. You can see that already, I think. I am going to match it with a regression problem, and in regression we always consider the regression coefficient as beta. That's the generic notation. So what is my problem now? My problem is I want to maximize expectation of, so now I want to convert it to a maximization problem just for the sake of understanding, because maximization is intuitively more natural to us. So I put a minus sign in front of the variance, and I also put a half here, again for obvious reasons. So when I take derivatives, it will cancel out the 2 that I get. So this half is just a convenience choice, and this beta is a choice to match it with the regression setup. So I have specific coefficients here for matching purpose. Otherwise, they are nothing particular. So I maximize expectation of minus half V1 square plus beta V1. Of course, I am starting with small v initial weight. Is this okay? Is the optimization problem fine?
Yes, sir.
And of course, I have this risk neutral condition. Expectation of delta Sn star must be 0. So then, if I look at this argument inside and match it with my original OPP, I can say that my utility function is basically this quadratic utility function. This is my choice of utility function, quadratic. So this choice of utility function matches with the variance minimization problem. So if I want to establish the variance minimization problem as my utility maximization, then my choice of utility function will be this. Minus half V1 square plus beta V1. That's my utility function. So then we go about the usual utility maximization, and we can do it. You know, Nohonil has already said, we know how to do it. It's easy. So rather than actually trying to do the algebra, let me tie in with the other side. The other side is the statistical side, empirical side. So suppose I started out with the assumption that the return vector follows multivariate normal. So if I start with multivariate normality and then do a maximization problem, because it's multivariate normal, the mu and sigma will be sufficient. So from there, I will actually come to this quadratic optimization problem. Is that clear now? Is this connection clear? This multivariate normality is actually consistent with the quadratic utility that we are talking about. And why do I choose the quadratic utility? Because I am in the mean variance setup. So the mean
Yes, sir.
The mean variance setup is essentially to be consistent with multivariate normality. maybe not only the normal distribution, but normal distribution is the most common candidate. So here what will happen is when we look at marginal utility, it will become a very nice function minus v1 plus beta. But we must remember that there is no reason why this cannot be negative. In real data, I may find a situation where u prime v1 becomes negative, but that is not allowed in the classical economics utility definition, because the utility function always has positive marginal utility. Del u del c1 was always positive. So there is a little bit of conflict here with the canonical assumptions of increasing marginal utility. Sorry, positive marginal utility. But for empirical convenience, we usually ignore this and go ahead with our mean variance setup. So the mean variance setup is not theoretically watertight, but it is so convenient that we still keep using it. Convenient because it ties up very nicely with the normal distribution in statistics. And obviously we know a lot about how to do statistics when the distribution is normal. So there's a lot of convenience here. So because of the convenience, we ignore this little theoretical problem. In fact, once you start looking at data, you will also see that the fundamental normality assumption itself is questionable, because the returns from financial data often have very different properties. In particular, financial returns very often show heavy tails. You know what that is, and heavy tails essentially nullifies all the convenience of normality, remember, because there may not be any moments existing at all. So empirically also, we see situations where normality is highly questionable. Theoretically, we see that the quadratic utility function has some technical problems because of the original canonical assumptions, but we have been using this a lot, and we will keep using it in future also because of the convenience of the whole structure. Because the optimization problem is very elegant, and we have a normal distribution as a backbone of the empirical work, which we are very comfortable with. In fact, later on in this course, I will be inviting some experts to talk about the models which are departures from this normality assumption. When we have, say, heavy tails or some other problems, we cannot use the normal distribution. How do we mathematically model financial prices? That we will learn later. But let us do the easy thing. The easy thing has problems both on the theoretical side as well as on the empirical side, but it is still so convenient, it is the most popular setup. So now I am not going into the details, so I will just state the optimal solution. The optimal solution will be affine. You can see that because it's a linear quadratic setup, and this is the particular form of the solution. So optimal V hat will be given by this constant beta by expectation of L minus L. So this is the linear dependence on L plus another linear term here. So again, I will ask you to do the details, work out the little bit of algebra that has gone in between the first order condition and then solving it. But if you do that, this is the kind of solution. This is the solution that we will get. Is this clear?
Yes, sir.
So it's a linear quadratic, so you know it will be affine, but the actual form, you have to do a little bit of algebra to explicitly find. The actual form will be like this. Now, for consistency, I must have expected V hat equal to small v into 1 plus rho, because that was my original constraint. That is the constraint I started out with, that I have a target return. So I plug that in here, and then I can solve for beta, because beta was the unknown constant, the Lagrangian constant, and if I solve it, I will get beta equal to this thing. So again, it will be a relatively simple function. It depends on 1 plus rho minus 1 plus r. So r is the bank rate, remember. So this will be the form of the solution. So basically this beta will go back to 2.33. It will get here, and we will get the final solution. The final solution after some simplification, because I can club things together, it will look like this in terms of the return. Instead of v hat, I can now write the solution for r hat, because return is what I am actually studying. So r hat will have this particular form. So this is the constant part, and this is the linear part, coefficient of L. So again, just check this and let me know if this is fine. It's just a little bit of manipulation, nothing else.
Yes, sir, it is coming out.
This is okay?
Yes, sir.
Okay, thank you. So you should check this thing. So this is my form of the return. So optimal solution is an affine function of the state price density L. Now let us combine this with this last equation in chapter 1, 1.35 that we discussed earlier when we said that this is going to lead to the capital asset pricing model. That was the covariance between H and H prime. So if you recall, let me show here on the screen. Right. So this was the equation. This expected RH minus R equal to this covariance by variance, which is the regression coefficient, times expected RH prime minus R. So the excess return or the risk premium on these two portfolios are linked through this regression coefficient between the two portfolios. So this is the regression coefficient, and these are the two excess return or risk premium. This we discussed last week. Now I want to tie this one with what we have found out now from our quadratic optimization problem here. So if I combine this R hat solution with the earlier regression equation, what we get is actually the capital asset pricing model. So what is the statement formally? The statement is if R prime is a solution of the mean variance portfolio for a target rho. So I have to fix a target and I will get a corresponding solution R prime. And now if R is the return of another arbitrary portfolio for some other return, then the returns will be linked. The returns will be linked through this regression equation as in 2.38. So the risk premium for R and the risk premium for R prime will be linked through this regression coefficient. Now this is a very, very convenient result. It is extremely convenient because you see the mean variance portfolio problem, even though it's theoretically simple, it takes a bit of effort to solve for a large system. If you have a large number of stocks for a large system, solving it takes some numerical effort. So you really do not want to do it time and time again. So whenever you change the target return by a little bit, if you have to solve it from the scratch all over again, it's a bit of a hassle. So this capital asset pricing model regression equation gives me a very nice bypass to it. So all I need to do is just find the regression beta of the new portfolio on the earlier one. So So earlier one R prime, I have already found out the solution. All I do is I regress R on the earlier portfolio R prime, and I get the relation between the risk premium. So I don't have to solve the whole optimization problem again. All I need to do is look at the regression coefficient. So that's why this is called the security market line or capital market line, because it gives me a complete locus of all the solutions. This gives me a complete locus. It's actually a line because it's an affine thing, as we have seen here. So for instance, suppose I have a new target rho prime, and I want to find the corresponding optimal return vector. All I need to do is relate it through this affine structure in this optimal solution, and I can actually write it as a linear combination. So if you think about it, I can simply write it as a linear combination of the earlier solution and the bank rate. So again, is this clear? Just think through this thing. It is actually a familiar setup, so I am not showing you the details at all. I think you can work it out very easily, but the intuition is important. The intuition is very important. That you really need not solve the problem again and again. The only thing that is required is the regression setup, because it's a linear, it's an affine solution. You are in the regression setup, and all you need is the beta.
Yes, sir.
So is this clear? So I started out with the quadratic optimization, and that gave me this affine solution for R hat. So I exploit this affine nature of the solution to tie in the capital asset pricing model here, which is the regression equation, and say that for any other target return, all I need to do is simply look at the regression coefficient. So I need not solve my problem again. It will just be a linear combination of the earlier portfolio and the bank rate. So I can redistribute between the earlier portfolio and the bank rate and achieve whatever new target return I want to achieve. And it will still be the minimum variance solution. So is this clear?
Yes, sir.
Anyone who is confused with this? Because again, these two are the most important structures in financial asset pricing. The one that I discussed earlier about the constant risk aversion setup, and this one, the mean variance setup, which leads to the capital asset pricing model. Because all through financial math literature, these are the two building blocks which we'll be using repeatedly. So if anybody has a doubt, just ask me, because we need to be clear about these two blocks. If these are clear, then the rest of it will be just extension of the same concept in a slightly more general scenario. Okay, so I take silence as understanding conveniently. So what we have done so far, let me recap. We are in the mean variance portfolio analysis. So what are you doing? We are essentially trying to minimize variance given a target return, which is equivalent to maximizing the expected utility under a quadratic utility function. And this quadratic utility function has some theoretical problems of negative marginal utility, but we ignore that because it is so convenient. The quadratic utility function connects us with the multivariate normal setup in empirical work, which is also very convenient. And it also has problems because we often see financial data with heavy tails. So normality is not as common as we presume. So there are problems on both sides, but even then, this structure of multivariate normality on one side and quadratic utility on the other side is so convenient that it is still the most popular model in finance. That model obviously leads to an affine solution because it's a quadratic objective. The affine solution for the return, optimal return vector is given by this equation here at the bottom of this page. And looking at the structure of this solution, we also figure out that if we want some other target to achieve, then all we need to do is mix the old optimal portfolio, original optimal portfolio, and the bank in a particular combination, in a particular convex combination to achieve the new optimal portfolio. So I have solved it for a target rho. To solve for a new target rho prime, all I need to do is mix the earlier optimal portfolio and the bank. Because of this affineness, I have this property. And the mixing coefficient will be essentially dictated by the regression coefficient between the earlier portfolio and the new portfolio. This is called the capital asset pricing model, and the resulting locus is called the security market line or capital market line. So what is the overall finding, or the overall message of this? The overall message is so important that we state it as a theorem. It is called the mutual fund principle or two fund separation theorem. What is this theorem? It says that if solution of 2.28, 2.28 is my original quadratic problem here. This is my 2.28. So if solution of 2.28 for some mean return rho is fixed, I find it h hat, then solution of this same 2.28 for any other mean return rho prime, new target, will be given by a portfolio consisting of investment in the bank, the riskless security, and the portfolio h hat. So I use the old h hat and the bank, mix them to achieve anything else that I want. And from a minimum variance solution, I will go to the other minimum variance solution without actually minimizing it. So I am guaranteed the minimum variance locus on this line. So that is what is called the two fund separation theorem, because even though the portfolio space has capital N many securities, a large number of stocks, once I have found the optimal solution for one problem, then it becomes only a two-dimensional problem. I have one portfolio H hat and I have the bank. So I need not look at the other stocks in separately at all. All I need to focus on is this portfolio and the bank. So I just need to mix these two things and I achieve whatever I want. Is that clear? Is this clear to everyone? Please respond. Or if it is unclear, just ask me and we can discuss this again. But if you don't tell me anything, then I am in a fix. Am I audible? Am I audible?
Yes, sir, you are audible.
Yes, sir.
Yes, sir. Yes, sir.
So would you please respond to my question? Or do you need a little bit more time to think? What is the response, please? You see, as I said, In the classroom, I can look at all of your faces, but now it is no longer possible. So I don't know whether I am getting through.
So this is clear to me. I don't know about
Sorry?
others. This is clear to me, but I don't know about others.
So specifically, if anyone is unclear, please ask me. So it's the other way around. This is a familiar structure. So for many of you, it will be very clear. The algebra is, I would say, elemental. But if somebody is unclear about the objective and the logic is the important part here. If anyone is unclear, please ask me. Because as I said, this is one of the two most important building blocks in this topic. Because if you don't ask me anything, I will assume that it is clear to all of you and move on. Okay, so then I make that assumption that it's clear to all of you, because I want to discuss something else.
স্যার পড়ে নিয়ে পরের দিন জানাই
Sorry, come again.
পড়ে নিয়ে পরের দিন জানাই মানে আরেকবার গো থ্রু করব অনেক কিছু হলো আর কি যা হচ্ছে
Okay, fair enough. So let me move on, but next day we will come back to this point and I will ask this question once again. Okay, fine. So let me talk about the departure from our original assumptions a little bit. And this is one of the most important departures. So far, we have been working under the assumption that my H values are all between 0 and 1. So, which means I cannot take a loan from the bank and I cannot sell a stock which I don't have. So I cannot have a negative weightage on a stock. Now it sounds odd, but in the financial market, this is called a short sale. A short sale is when you are notionally selling a stock to someone else, but you actually don't own the stock. How does it work? Basically, it works in the following way. When you make a short sale, you have a limited amount of time within which to acquire the stock and fulfill your obligation. So the person who is buying from you is not immediately taking delivery. There is some time window, but it's a small time window. So by the end of the time window, you must have that stock so that the person who has bought it from you and comes to claim it, you have to hand it over. So in a short interval of time, you can have a negative weightage of the stock, and that is called a short sale. So we have worked with these constraints to begin with. No short sales, no borrowing from the bank. So which means all the HNs had to be non-negative. Now we are defining a new symbol F, because in the invariance portfolio setup, we talked about the return and we talked about the solution in terms of small f. So what we do is we define Fn as the fraction of wealth invested in the stock. You see, V0 is my whole wealth on day 0. And how much do I buy of the stock N? I am buying Hn times Sn0 amount of value of this stock. So Sn0 is the price and Hn is the quantity of the stock. So what I spend on stock N is Hn into Sn. So the fraction of my wealth going into stock N is defined as Fn, which is this amount divided by V0. That is just a redefinition for our convenience. And similarly, we have F0. F0 is the fraction of wealth invested in the bank. So initially we assume that all the Fn's are non-negative and bank F0 also non-negative, so that summation of our Fn must be less than or equal to 1. So this was the original setup that we worked on so far. Okay, is that clear? This is just the original constraint redefined in terms of fraction of wealth, nothing new. Now, what are the typical realities which depart from these assumptions? The typical realities could be that I do allow a little bit of short selling, a limited amount of short selling. So I allow Fn to be negative, but maybe not too much negative. Sometimes I also allow for short-term borrowing, so that F0 can also be a little bit negative for a short amount of time. In general, there could also be some investment priorities. Investment priorities are, for example, that as an investor, as a portfolio holder, you must invest at least 20% in the State Bank of India stocks. You see, often investment houses have these constraints to honor, that they must invest a minimum amount in government securities, a minimum amount in very safe bank deposits, like that. So those constraints are also essentially constraints on Fn. So in general, a notation for that would be, suppose A is a set of the priority sector stocks, where I must put at least alpha lower bar amount of wealth. So the aggregate investment in sector A, which is given by summation over Fj j in A, must be at least alpha 1. So these are called priority sector investments. These are also very common constraints. And obviously, these constraints complicates our optimal solution. Okay. So mathematically, what are we looking at? Mathematically, what we are looking at is the following. The constraints of interest are of this form, F equal to F1, F2, Fn vector, belongs to some set K, and this K is a subset of Rn, but not equal to Rn. You see, now I am saying Rn, so I am actually allowing some negative numbers, but obviously it's not unlimited. It is actually restricted to some set capital K. If I put my capital K as the positive orthant, then we are back to our original setting. In our original setting, we are working with only the positive orthant. Now what I am saying is that life is not usually so easy. We normally have to allow some parts which are outside the positive orthant, which have some negative components to some extent. So K is actually more than just the positive orthant, but it is also not the whole of Rn. There has to be some restriction. Okay so far?
Yes, sir.
Where are you incorporating the assumption that Fj cannot be negative for too long?
Fj cannot be negative for
Too long, that you said that it cannot be too much negative and it cannot be negative for too long.
So right now we are in a static setup, so that too long part we are ignoring for the time being. You see, we have only one time point, 0 and 1. So right now for too long part is not really going to hit, but not too much is going to hit in the set capital K. The time part we will tackle later on. Right now it's a single period market. Next time we will get into the multi-period market. Okay, so hold that too long part. Now it is only that not too much part. So now, under what minimal assumptions can I still solve my problem? There are some minimal assumptions that I still need. Otherwise, I just cannot solve this problem. I need to somehow ensure that I can use the usual convex set arguments. You see, this is the linear quadratic problem, and if I have a convex domain, I am guaranteed a solution. So somehow I need to reconstruct that convex domain argument. Otherwise, I am lost. So what are the minimal structure that I need? The minimal structure is essentially something like this. That K is a union of closed convex sets, and the zero vector belongs to K. Why do I need the zero vector? The zero vector means I am putting all my money in the bank. Remember, whatever remains goes to F0. So if I have the zero vector as my choice of F, that means F0 is the whole, all of the wealth. F0 is visible. So this is the minimal restriction I need for obvious reasons. You understand this? You do, right? It's clear.
So sir, you are not in the summation Fj belongs to A greater than equals to alpha, that you are not considering that problem, but generalizing that to an arbitrary K.
Yes, but if you see that the summation Fj greater than equal to alpha lower bar will be a special case here.
Right. I mean, that is always convex. My question is that is it always convex? Why are we?
That is always one. Yes, yes. But what I am trying to locate is the best possible domain where I can work. Rather, the biggest possible domain. See, earlier we had only the positive orthant. Now I am trying to extend as much as I can. So this is the biggest possible domain. So my constraint problem is formalized in the following way. So this is a little bit conceptual. So just follow this carefully. My problem is essentially I want to maximize over this set capital K, not the whole thing. Objective remains the same, but recast in terms of return. So I am writing Fn Rn minus R here instead of our usual Hn Sn, such that V0 is small. So this is my constraint Lagrangian problem. How will I solve it? Because K can be complicated. How do I do it? So now recall the risk neutral computation algorithm that we had earlier. Okay. So for the risk neutral computation algorithm, we can talk about a constraint portfolio problem also. So what do I do? Take any small k in capital K. So it's a single point market, very trivial. Define a modified market M sub small k. So it's a very simple market. You can solve any problem there very easily. Solve the unconstrained problem for M small k. That should be easy. Suppose the solution is tau k at V. V is my initial wealth, so it will depend on the initial wealth. Tau k V for small k. Then solve the dual problem. What is the dual problem? I have all these optimals. It's like an envelope. So what would be the optimal for the whole set capital K? It will be the minimum over all the small k's. So that would be my constrained optimization strategy. So I solve it for very small markets, trivial markets, collect them together, solve the dual. So is this clear? I had a constraint problem with some restrictions. To solve it, I take recourse to the risk neutral computation approach, but in a twisted way. I define very small markets, very easy markets, solve the problem there. Then I collect all the solutions, all the small market solutions, and solve the dual problem. Minimize the optimal over all those small markets. That's my strategy for solving the constraint problem. So is this clear?
Yes,
of
sir.
course. Okay, thank you. So we will get back to whatever questions you have next day. But essentially, this is the single period optimization problem in two versions. One is for the constant risk aversion utility setup, which becomes scale free. And the other one is the mean variance setup, which is consistent with the normality assumptions in empirical work. And we also look at how we can go around if some of the original domain restrictions are removed, in the sense that we are allowed borrowing, we are allowed short selling, or we have some priority sector constraints. So all these kinds of constraints can be accommodated in the optimal solution. It will take some more work. As we can see, it is quite a bit more work, but a reasonable solution strategy is still available. So the exercises from chapter 2 are 2.1 to 2.4. Again from Pliska. And of course, all the examples that are worked out in the chapter. So these you should start working with. The chapter 1 problems examples as well as the chapter 2 problems and examples. I will stop today, and Wednesday we will start the next chapter, but before that we will discuss whatever questions you may have. But at this point, the onus is on you. You have to study, you have to come up with questions, whatever doubts you have. Look at the book, because as I said, my note is neither necessary nor sufficient. Look at the book, start looking at the examples, so that Wednesday you can come back to me with whatever doubts and whatever clarifications that are given. Okay, so unless you have some quick questions at this point, we will stop. Okay, all right. So let's meet Wednesday then.